All right, today we're going to talk about FPGAs and their applications in machine learning. This is brought to you by Callie Carter and Charles Hayden K. Wilson.
What are FPGAs, you may ask? They are field programmable gate arrays, and these are semiconductor devices that have a matrix of configurable logic blocks, or CLBs. These CLBs are interconnected, and these interconnections are programmable. These interconnections can be programmed after manufacturing, and they can be reprogrammed again and again.
And here we have a picture of the Altera Cyclone 4, which is one of the newer FPGAs out there. A little bit on the history of FPGAs. We kind of saw a rise of EEPROMs and reprogrammable logic devices were already on scene, namely those made by Altera. Those were followed up in 1985 with patents for logic blocks and a couple other similar technologies by LeTourneau R. Peterson and David W. Page. And then after that, we see the initial FPGA patented by Steve Castleman in the late 1980s. The experiment that he devised these from were funded by the Naval Surface Warfare Center, and it would consist of hundreds of thousands of reprogrammable gates. Surprise, surprise, it was a huge success. There's a picture of Mr. Castleman. This was a step up in reprogrammable logic. With the rise of various forms of memory in the 1980s, the reusability of EEPROM set the stage for what eventually became electrically reprogrammable logic devices cumulatively. EEPROM was first reset or erased with UV light via the middle window, whereas FPGAs were programmable and reprogrammable using VHDL and whatever programs supported that, or Cordis and things like that Altera ended up making. There you see EEPROM with the little window there, and then Cordis 2 is one of the softwares used early on for FPGA programming.
FPGAs have some applications in the field of machine learning. So they tend to be used for inference more than training. Training is the stage in which a machine learning model is created and then learns from test data. This is accomplished by running the data through the model while knowing the correct output. And after you get a model from your output, the error is backpropagated through the model in order to adjust things until the correct output is eventually given by your model. Inference is using this trained model or algorithm to analyze new data and make predictions off of it. FPGAs today are mainly used for inference because of their strengths and weaknesses. They have limited floating point capabilities, but they offer higher performance with lower precision computation than GPUs tend to. So it is helpful. Another strength is that inference is typically a part of larger applications that originate without machine learning. So analyzing genomes, filtering signals, and video surveillance tend to use FPGAs already. So all you have to do is add some more programming to the logic, and it will update their functionality. So FPGAs are being used in inference because they excel in raw computational power, especially with their less intensive floating point performance. They are improving in the area of floating point performance, however. They also excel in handling multiple data types, including custom ones. Because of their underlying hardware logic that can be programmed in, FPGAs are faster and more power efficient with computation and the analysis of data. So in inference, many kinds of data need to be analyzed at a quick pace to make real-time predictions, especially with applications such as autonomous driving in cars. So the strengths of FPGAs make them a desirable hardware solution for these needs.
All right, for FPGAs for the future, as we continue to encroach upon the end of Moore's Law, whether accurate or inaccurate, which for those who don't know, Moore's Law is the observation that the amount of transistors that you could fit on a single chip would double every however many years. I think it was every 2 years. And we've started to see that has hit a cap and is no longer the case. That was accurate for about 10, 15 years, but is no longer the case. Something else will have to drive this innovation. Transistor size can't get much smaller, and consumer electronics tend to push for a smaller form factor, and software, especially AI and machine learning, can be developed endlessly. So what gives? New focuses seem to be algorithm efficiency, adaptability of hardware, and rapid iteration / machine learning for efficiency. If we can't get more raw power efficiently in computing the way we've been doing it, why not be smarter in how we use the capabilities in existing technology? Surviving the death of Moore's Law. Some future FPGA examples. Currently, as the U.S. government's cloud-based computing and cybersecurity efforts have been moved from Amazon to Microsoft, somewhere in the woods outside of Seattle, every node of Microsoft's Azure platform has its own FPGA. Azure is a cloud computing platform. Some say, namely the guy who owns the patent for the first FPGA, that we are seeing a move from off-chip computing with overhead from data transfer and traditional computing, that is the von Neumann model, to a new FPGA-based computing future. There's even a paper by some students at Boston University on the subject. Here's our list of sources and websites that we used. As well, this was prepared for digital electronics for LeTourneau University. Alrighty, thank you so much.